We are continuing on with electrolytes in this chapter. It's a pretty big chapter, but anyhow. So electrolytes again, in this one we will focus more on acid-base reactions, which are also called neutralization reactions, and oxidation reduction reactions, which are also called redox reactions for short. Initially you might find some things that are a little repetitive, so if you didn't understand them before, go ahead and listen to them again. If not, just go ahead and forward it and go on to the things that are new for you. So now for the different kinds of reactions that can actually take place, okay, in water. We've talked about different classifications before, and I'm going to introduce one more, okay, to you. So there are two different kinds of classifications. The first one that you have done is the atomic rearrangement, which was the synthesis, in which case you combine two things and get one thing. A double displacement, in which there is two exchanges going on, that is called double displacement. Then we talked about a single displacement, in which case one element would displace the other one, okay, and so you would still have the same number of chemicals on either side. And then decomposition, in which you start with one compound and you end up with two products in the end. That's decomposition. It's the opposite of synthesis. This is what you did in the previous chapter. In this chapter, we'll talk about the chemical reactions that are taking place, not in an atomic form, but in a chemical way. And the chemical reactions are classified into three: precipitation reactions, okay, where a solid is formed; neutralization reaction, when an acid and a base will react to form salt and water; and then oxidation reduction reactions, in which case we talk about either the addition or removal of oxygen or transfer of electrons. Okay, so this is a chemical classification, and this is what we will focus on for this chapter, okay, for the first part of this chapter. Here are your examples of strong acids. The most common acids that you will encounter are going to be hydrochloric acid, nitric acid, sulfuric acid. Okay, these three are the most common ones. The other ones are also strong, but you don't encounter them so much in general. Okay, and don't worry about this equation at the bottom. You will talk about this one more in Gen Chem 2, not so much right now. Okay. But hydrochloric acid, nitric acid, sulfuric acid, remember these are strong acids, which means they dissociate completely. The second type of reactions are neutralization reactions, which are also acid-base reaction. To understand acids bases, let's go ahead and learn a little bit about them before we start writing reactions. There are two definitions for acids and bases. One is Arrhenius and the other one is Bronsted-Lowry. The Arrhenius is the first definition, and in case for acids, the Arrhenius acids are the one that give H+, okay, which is a proton when dissolved in water. Hydrogen ions are known as protons because the hydrogen ions have only two particles, a proton and an electron. And if the electron is given away, as in a cation, then all you have is a proton that's left over. So a hydrogen ion sometimes is also called a proton. So Arrhenius acid is something that gives a proton when dissolved in water. Arrhenius base is something that produces hydroxide ions when dissolved in water. That is the old definition. The new definition of acids and bases is the Bronsted-Lowry acid and base. And this is the same as the Arrhenius acid definition, which means that an acid will donate a proton. Okay, and this is an acid. The Bronsted-Lowry base, however, is something that actually accepts a proton, okay? And so that is called the Bronsted-Lowry base. Some of the other properties of acids bases that you might want to be aware of is that acids are sour. For example, fruit juices, these are all sour, and bases are bitter. And an example that I can give you of a base here that is bitter, if you have ever tasted this, and you must have, soap. Okay, and if you were, when you were a child and you may have swallowed some soap, it was not very tasty. Okay, and that's bitter because soap is a base. Okay, and most bases are going to be bitter. So acids are sour, bases are bitter. Acids cause what we call corrosion, okay, and they are corrosive in nature, whereas bases are caustic in nature and they are slippery. Okay, so when you touch a base, your fingers actually will feel it, and just like soap. Okay, corrosive and caustic, these are both burns, But because they're both burns, they have to classify them as acidic or basic, because then that's how they are treated. So you have to be specific, okay, how you got the burn. So if it's acidic burn, it's called corrosive, and if it's basic, it's called caustic burn. A pH value is a measure of how acidic something is, and the pH value for acids is 1 through 7, and a pH value for bases 7 through 14. Again, you will learn more about this in Gen Chem 2, but pH is just a measure of how many hydrogen ions you have, okay? And so 1 through 7 is when you have more hydrogen ions, 7 through 14 is when you have more of the hydroxide ions, okay, or less of the hydrogen ions. Examples of acids, the strong acids are the ones that completely ionize in water, and you already have a list of it from before. And the ones I said you will need a lot more are nitric acid, sulfuric acid, and hydrochloric acid. These acids, the other ones, they're also there, and these are also strong acids, but again, as I said, you don't encounter them so much in general chemistry. And sometimes even later on. They're very specific, okay, in their uses. However, nitric acid, sulfuric acid, and hydrochloric acids are very common strong acids that you will encounter in your general chemistry experience. Strong bases, these are all the hydroxides. So potassium hydroxide, sodium hydroxide, calcium hydroxide, these are all considered to be the strong bases. And see, I mean, it's very easy to figure out if it's a base or not, because they all have hydroxides in them. And then there are the weak acids, okay, which means that they ionize only partially in water. They're not completely ionized. And one of them is acetic acid, okay, and you'll encounter it quite commonly, okay. Acetic acid is found in the common vinegar. Hydrofluoric acid is not a very common acid, okay, that you will encounter. So, but you still know it now. The weak bases are ammonium hydroxide, some of the carbonates, okay, like sodium carbonate and sodium hydrogen carbonate. These are considered to be weak bases, and some of the organic bases. And again, if you don't know this part yet, it's all right. You will encounter it again in Gen Chem 2. But acetic acid, you might encounter it this semester also. So these are your properties of acids and bases. There are some things that I really need you to know in this, okay? And these are the definitions that I need you to know, and I need you to know this part, okay, of the examples of strong acids and strong bases, and the weak acid and the weak bases. Here are some of the common acids, bases that you might encounter in your life in general, which is salicylic acid, which is aspirin. Acetic acid, as I said, this is the common vinegar. Citric acid is found in fruit juices most of the time, and orange juice, which Florida is famous for, you will definitely find citric acid in there. Some of the common bases, magnesium hydroxide, which is the milk of magnesia, Malox, sodium hydroxide, which is Drano, and what's not shown over here is sodium carbonate, sodium bicarbonate, which is the baking soda. So a little bit more about acids and bases is that almost all acids and bases will look like water, okay, which means that they are clear and colorless. So how do you tell them apart? Okay, that comes a big question. And one of the ways you tell them apart is by using an indicator. An indicator will give a different color for strong acid or a weak acid, strong base or a weak base. So you use the appropriate indicator for the appropriate acid and base. And this takes a little bit testing, but it can be done. One other thing I want to mention about acids, and this is something that I skipped before also, and I mentioned that I will talk about it again later, is polyprotic acid. Okay, so when we have something like HCl, which is hydrochloric acid, it has only one hydrogen to give. But some acids like sulfuric acid has two hydrogens to give, and these kind of acids then are known as polyprotic acid. And if it has two hydrogens to give, it will be called diprotic. If it has three, it will be a triprotic acid, and so on and so forth. So right now we don't have to worry so much about the polyprotic acids. You just need to know that they can give two protons. Now for the acid-base neutralization reaction, the actual reaction itself, all acid-base reactions will be double displacement reactions, just like the precipitation reactions. If you have the traditional acid and base, which means something like HCl, something like a hydroxide, then you will always have salt and water as one of the products. And some of the carbonates and sulfides, they end up giving some gases as products. So carbon dioxide and sulfur dioxide, these gases are produced. So depending on what kind of an acid base you choose, you can have a little bit of different results. In these slides, in the coming up slides, I've given you examples of everything. This is a simple acid-base equation here. So we'll take the traditional acid plus base to give us salt and water, which here is HCl plus NaOH to give NaCl plus H2O. So hydrochloric acid, sodium hydroxide, sodium chloride, and water. Note that everything is AQ, 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 and then water is liquid. Okay, all the other species are dissolved in water, but water is just water, so it's liquid. Okay, and water is one of the products then. We write the ionic equation, which is H plus, that's the proton, which HCl has dissociated into giving H plus and Cl minus. Sodium hydroxide gives sodium ion and then hydroxide ion. And then on the product side, you have the sodium ions, the chloride ions, and of course the water that has not dissociated. So then the net ionic equation is H plus OH minus to give H2O. So protons plus hydroxide to give water. Okay, again, you have to cross out the spectator ions, okay, which is sodium and then chlorine. Okay, these are the spectator ions that we have. So let's write an equation now between sulfurous acid and potassium hydroxide. So another example of an acid-base reaction. So first of all, write the molecular equation. Sulfurous acid is H2SO3, not H2SO4. SO4 is sulfuric acid. Okay, and so this is H2SO3 plus potassium hydroxide gives water and potassium sulfite. The first thing to do is to balance the equation. Okay, so balance the equation out, put the coefficients in there. The next thing is make sure you write your AQs and your liquids, AQs, okay, over here. Then ionic equation, the sulfurous acid, not very dissociated, okay, in a reaction because this is a weak acid. It does not dissociate. It is dissolved in the water, but it is not dissociated completely, okay. And this is an example, and I'm telling you this, I probably will not give this to you on an exam, but this is an example so you know how things are written in case some chemicals are not completely dissociated in the water. So here this is not completely dissociated in the water. It's still there a little bit, okay, not too much though. And then we have the potassium ions, the hydroxide ions to give water as a liquid, and then the potassium ions and sulfite ions, okay, in the solution over here. And these ions are coming from the sulfurous acid from whatever was dissociated, okay, little bit that was dissociated in here. So then the net ionic equation is sulfurous acid that is not dissociated plus the hydroxide ions, okay, and water and the sulfite ions, okay, because in this case your common ions are only potassium, okay, you don't have sulfite on the left side and you don't have sulfurous acid on the right hand side, okay, and so all of this is part of your net ionic equation then. And this is just an example to show you that not everything gets crossed out because not everything is ionized sometimes, okay, and so you should be ready for that also. Again, I may give that to you as a multiple choice question, but not maybe as one to write out. Here are some examples of some neutralization reactions that produce gas. Okay, so for example, when you take sodium sulfide, treat it with the hydrochloric acid, and you end up getting H2S, which is hydrogen sulfide as a gas. The carbonates and the sulfides, they will always give gases. The carbonates will give carbon dioxide, the sulfides will give sulfur dioxide. Okay, the carbonates here can be also hydrogen carbonates that will also give carbon dioxide, okay, as one of the products. When you write these reactions out, again, mind the AQs, everything is dissolved in water, but then when you come to the right-hand side of the equation, you have to be careful because the gases are indicated as G. So again, they are not in solution, okay, they are indicated as G. This here is just a visual representation of a base and an acid to give salt and water, and then of course the gas, okay, that's in there. So this is baking soda, which is sodium hydrogen carbonate with acetic acid. You should write this equation out, obviously. And to give the product, I will leave that to you, and then carbon dioxide also as a product. So let's go ahead and write an equation out for one of the gas equations here, okay? So copper 2 carbonate, CuCO3, which is a solid, okay, and it's being treated with hydrochloric acid to give copper 2 chloride, which is dissolved in water because all the chlorides are soluble in water, not all, but copper is. And then water, which is a liquid, and then carbon dioxide, which is a gas. Okay, so this is our molecular equation. How did you know that copper carbonate was solid? I will have to tell you that. Okay, so I may give you this equation and then I can ask you to write the ionic equations. Okay, or I will tell you whether the copper 2 carbonate was a solid or aqueous solution. Then the ionic equation is written out like this, where you have the copper 2 carbonate, which is still a solid. The HCl, hydrochloric acid, will dissociate, okay, and ionize into these two ions here. Remember again, this is 2H plus and then 2Cl minus here. The copper chloride, which is aqueous, again copper 2 plus, and then the two chloride ions, again remember not Cl2 but 2Cl minus, okay, and then the water and the carbon dioxide, they stay as they are because they're not aqueous, okay. And so the net ionic equation is that of copper 2 carbonate plus the hydrogen ions to give the copper 2 ions, water and carbon dioxide. The only common ion here is chloride, okay, and so you cross that out, that's the spectator ion, and then you have to write the rest of the equation out. So not as simple as what we were writing before, a little bit more involved, okay, and has a lot more chemicals in it than what we were doing before with simple acids and base reactions. Now let's look at the third category of reactions, which are called the redox reactions. Redox reactions are oxidation reduction reactions. Ox for oxidation, red for reduction, okay? So let's look at what is oxidation and what is reduction to begin with. First, simple definitions. Oxidation is addition of oxygen, which means any chemical that adds on oxygen is undergoing oxidation. Reduction is the opposite of oxidation. So if addition of oxygen is oxidation, removal of oxygen is reduction. Similarly here, reduction is addition of hydrogen, which means oxidation is removal of hydrogen, which means that any chemical that is missing a hydrogen on the product side has undergone oxidation. The last definition for oxidation and reduction is by electrons, okay? And so loss of electrons is oxidation. So anything that loses electrons is undergoing oxidation. Anything that is gaining electrons is undergoing reduction. This Leo and Ger, these are very easy ways of remembering what is going on as far as the oxidation reduction is concerned with electrons. Loss, electron, oxygen, Leo. Gain, electrons, reduction, Ger. Leo goes Ger. Anyhow, the loss of electrons, okay, is oxidation, and gain of electrons is reduction. So these are your three definitions, okay, that you need to know. Now, for a few other things that you need to know is that metals will always lose electrons. Remember, we've talked about this in chapter 2 also. So on the left-hand side of the periodic table where we have all the metals, they will always lose electrons and therefore will always undergo oxidation. The non-metals, on the other hand, will always gain electrons and therefore they will undergo reduction. Now, there is another classification that we do, and that is of reducing agent and oxidizing agent. Okay, so a reducing agent is something that causes reduction of another, okay, and it gets oxidized in the process. So it's reducing something else. That is why it's called a reducing agent. So if it is reducing something else, it must be getting oxidized. If it is getting oxidized, it must be losing electrons. That is why I put it in this column, okay, because reducing agents are usually going to be metals, because metals are the one that lose electrons because they're the ones getting oxidized. Oxidizing agents are opposite of reducing agents, which means that oxidizing agents cause oxidation of something else and get reduced in the process. Okay, so oxidizing agents cause oxidation of something else and it gets reduced. If it gets reduced, it means it's gaining electrons. What gains electrons? Non-metals. Okay, so all your reducing agents are on the left-hand side of the periodic table. All the oxidizing agents are on the right-hand side of the periodic table. If you ever forget this, okay, think of your oxidizing agent, oxygen, okay, which is on the right-hand side. That is the most common oxidizing agent, all right? And so you find that on the right-hand side of the periodic table, and it causes oxidation of something else. And that is an oxidizing agent. It's a non-metal, so it will undergo reduction, okay, which means it will gain electrons. So please know this table well. All of this is important in here, so you need to understand and remember all of this. Writing redox reactions. Redox reactions look very different from acid-base reactions and precipitation reactions, because in redox reactions, sometimes you're not really quite clear what's going on. So you really have to pay attention to the electrons, okay? Because there will be some other examples we will talk about, in which case you have oxygen being added and hydrogen being removed and all that. But a lot of the redox reactions that you encounter are going to look like this, in which you're wondering what is going on. Okay, well, in any case, the first thing is that look at this reaction. This is classified also as a single displacement reaction, right? Because you have zinc displacing copper to give zinc sulfate, and then copper as a solid. So one exchange going on here, that is a single displacement reaction, okay? So looking at this reaction here, you look at the common ion, and then hopefully now you're comfortable with finding the common ion, okay, the spectator ion, which is sulfate, okay, on both sides of the equation. So let's not write sulfate anymore in our ionic equation. We don't really have ionic equations in redox reactions. It's a little bit different kind of a reaction system, okay? But let's go ahead and take out the sulfate because these two are common, okay, on both sides. So that means you're left with zinc as a solid, copper as ions. Now remember, it is still bonded to sulfate. It's just there, okay? It's there, but it's, you know, a spectator ion. So you have copper ions, and then you have the zinc ions over here coming from zinc sulfate, and then the copper, which was a solid, okay? So this, in a way, is your net ionic equation, okay? So now let's look at this equation and see what is getting oxidized and what is getting reduced. Zinc here goes from zinc to zinc 2+. Here zinc was elemental, which means that it was neutral, okay, no charge whatsoever. But now it is zinc 2+, so it means it's lost 2 electrons. So if it loses electrons, this is an oxidation process. And then we have copper, which is going from copper 2+ to copper solid, which means that copper going from 2+ to solid, meaning it has gained 2 electrons, okay? 2- plus 2+ gives you neutral. So if it has gained electrons, it has undergone reduction, okay? So hence this is an oxidation reduction reaction by the way of gaining and losing electrons. Usually we write redox reaction as half reactions, okay? So which means that you separate out the oxidation reaction and the reduction reaction. So let's separate the one for zinc first, all right? So zinc is losing 2 electrons, so you write that out as zinc solid on the left side, and it is getting reduced, which means that it is losing electrons going to zinc 2+ to give 2 electrons. The electrons are written as product because that's what's given out. And then copper ions are gaining the 2 electrons, so this is how you would write the other half of the equation, which is then copper 2+ gaining 2 electrons to give copper solid. Remember, there are no minuses in equations, which means you can't write zinc minus 2 electrons to give zinc 2+. That is not a proper equation. You have to write pluses only, okay? And so zinc gives zinc 2+ plus 2 electrons. So in case of oxidation, you will find the electrons on the right-hand side. In case of reduction, you will find it on the left-hand side. Okay, and if you don't want to remember that, that's fine. Okay, also. Um, Visually, this is what it looks like. Okay, so you have zinc in here, which has been added. This is a copper solution. And so there's an exchange going on, and eventually copper is going to become the solid, which is over here, and zinc is going to be in the solution. Okay, that is how this works. So how do you know what charge anything has? So I told you about the zinc because it was neutral, it was an element, and that's why it was 0, okay? But how do you know that? And these are the rules here, okay? This is how you know what any charge should be on any compound or element. All the elements in their elemental state are 0. So for example, all the metals as they exist, like zinc, copper, sodium, potassium, as they will all be 0 charge, okay? The monoatomic ions will have +1. So for example, potassium ion, sodium ion, these are +1, okay, always. Oxygen is usually going to be -2. The only time it is not -2 is in peroxide, hydrogen peroxide, where it is -1. And you may encounter this in lab one time, but usually not in our coursework, okay, not so much, not in this semester. So oxidation number of oxygen is always -2. Remember, we've talked about this. This is in group number 6, and group number 6 has a charge of -2. Hydrogen can have +1 or -1. It depends what it is bonded with. What we mean by saying over here for hydrogen, it is +1 and -1, is that hydrogen can never be +2 or -2. Okay, it's always going to be either +1 or -1, depending again how it is bonded. Halogens are pretty much going to be -1, group number 7, okay, always going to be -1. In some cases, things are different, okay, and we'll talk about those exceptions when you have oxidation states for halogens which are not -1, okay, we will talk about that too. But for most part, if you're trying to figure out the oxidation number for a metal that is bonded to a halogen, then you will take the halogen as -1, okay? Compounds and ions, all right? The sum of any oxidation number that you might have on a compound is going to be 0, always. So sodium chloride, NaCl, neutral, okay, 0. No charge left for left. In case of the polyatomic ions, the charge that is left over is the charge that is on the ion. So for example, when you have hydroxide, which is -1, the charge that is left over is -1. Okay, so some of the oxidation numbers, when you add up oxygen and hydrogen in there, your final answer should come out to be -1. For sulfate, it's going to be -2. So when you add the oxidation numbers for sulfur and oxygens, your total should be -2. In a neutral compound, it is going to be 0. Okay, so that is how you assign all these numbers. We'll do a few examples now. In a minute. Okay, so here are oxidation numbers from the periodic table. You have this with you for most part. We did this in chapter 2 also. So except for hydrogen over here, which can be plus or -1, column number 1, which is the alkali metals, is always going to be +1. This is going to be +2. The transition metals are always different, remember, and we have to calculate those. Okay, but these are all the oxidation numbers for it. But remember, you don't have to remember this, okay? So it's fine. For group number 3, 3 plus. For 4, plus, -4, +2 for carbon also. And then these are the numbers given. You may want to print this out and keep it handy in case you need it, or you might have written it on your periodic table already, okay? Now, these numbers here that you see, okay, because remember we wrote out for group number 5, we wrote out to be -3. That is when it is bonded with a metal, okay? When it is not bonded with a metal, so for example in nitrogen dioxide, nitrogen trioxide, those are covalent compounds. In those cases, the oxidation number is going to be +1. The oxidation number does not mean that nitrogen is suddenly a cation, okay? It's not a cation, it is still an anion, okay? But the oxidation state, okay, the oxidation number at that point is positive. So remember these positives for the non-metals have nothing to do with whether it is a cation or not, because when you start forming covalent bonds, you don't have any cations or anions, okay? When you have ionic bonds with the non-metals, you will have the standard charge, okay? Which means that if you have a ionic bond with group number 5, it is going to be -3. With group number 6, it's going to be -2. Group number 7, it's going to be -1. It's only when they're bonded with each other in covalent bond, that is when they will have all of these other oxidation states. Okay, so we'll practice some and then you will understand what I mean. And again, remember, you don't have to worry about these ones because you'll have to calculate them. This is an activity series, as we call. We just did an example of zinc and copper, okay, where copper was accepting electrons. And if you recall a little bit further back, I mentioned to you that non-metals gain electrons, okay, which means metals always give electrons. So how is it that copper is actually able to gain an electron? Because technically copper is a metal. And if copper is a metal, it should only give electrons and not take electrons, all right? So I was wrong. No, I was not wrong, okay? This is all based on activity series, okay? Which means that there are some metals that are capable of giving electrons much more readily than other ones, okay? And the ones that give electrons can then go ahead and give electrons to other metals then, okay? So here, for example, lithium, potassium, they will give electrons very readily. So if there is any copper ion available at that place, that copper ion will take that electron immediately, okay? Because it's very much lower down in the activity series. So anything on the top here can give electrons, anything on the bottom can take the electron. Bottom here does not like to give electrons. Gold is one of the most inert metals, okay, that is out there. That is why all the jewelry is made of gold, because it doesn't do any reactions. So gold has a very hard time giving its electrons away, which is why it's on the bottom of the activity series. Okay, lithium on the other hand, you will never find lithium in nature because lithium always exists only as lithium ions, not as lithium metal. Okay, so all of these here on the top, these love to give electrons. Okay, and so they will give electrons and they will not exist as elements, they will exist as ions. Now you have encountered magnesium in the lab, okay? When you did the empirical formula lab, you encountered magnesium, okay? Which also you had to clean up a little bit because it will react, okay, with the environment, with the oxygen in the environment. You've also seen aluminum in the density lab. You've seen zinc in the density lab, which means that these elements can actually exist, okay, on their own, although they are reactive, okay, which means they will react with oxygen slowly. But as we keep going down, the reaction gets slower and slower, which means they get more and more inactive, okay? So higher loves to give electrons, lower loves to take electrons. So let's practice some oxidation states. We're going to start with a simple one first, which is magnesium bromide. Magnesium bromide, both of these elements are main group elements, so this should be fairly easy. Magnesium is group number 2, which is always going to be +2. Bromine, since it is combined with magnesium, it's an ionic bond, so it's always going to be -1. And because you have 2 of those, you multiply it by 2, so the charge is -2, total of -2. So +2 -2, you add them together, the charge should come out to be 0. And that is correct because this is a neutral compound. Let's take for chloride ion. Now this is an ion, okay, which means that you should have a -1 left over at the end. In this case, you cannot treat chlorine as a halogen, okay, which means you cannot have Cl as -1, okay. The oxygen is your standard here. You will always start with oxygen, which oxygen is -2, and it will always remain -2 except for peroxide, okay, which we're not going to be dealing with. But oxygen is always going to be -2, and you have 2 of oxygens over here, so -2 times 2 gives -4. The total charge should be -1. So the charge on chlorine then must be +3 because -4 + 3 gives you -1. That is the charge that is left over. Okay, so the oxidation state for chlorine here is +3. Okay, which is a little weird, I know, but then again, remember, we're not talking about bonding with metals here. We're talking about oxidation state, okay, which is a different thing. Assigning oxidation number for manganese, okay, in this one. So here's another approach, okay, for doing this. You have 1 of potassium, which potassium is +1. You have 1 of manganese, which oxidation number of manganese is what we're trying to figure out. And you have 4 of oxygen, which is -2. Okay, that is all coming from the formula, and -2 is coming from the group number. Okay, and so oxygen group is -2. Which means the total charge on potassium is +1. We still don't know the charge here. And the total charge on oxygen is -8. All of this should add up to be a 0, okay, for us. So you add up 1 plus -8, and that is equal to -7. -7 plus whatever the oxidation number of manganese just should be coming out to 0, which means that oxidation number of manganese is +7. Okay, because -7 plus 7 gives you 0. Okay, so that's the oxidation number of manganese then. Let's do another one here for chromate. And this is an ion, dichromate ion. Now remember here, this is 2-, which means that the residual charge at the end should be -2. So we have 2 of the chromate ions, so 2, and then the oxidation number of chromium. And then we have 7 oxygens, 7 oxygen. Each oxygen is -2. And so 2 number of chromate ions plus -14, 14 coming from the total charge of oxygen, it should be equal to -2. All right. So you take the -14 on the right hand side, okay, which is algebraic equation. And so if you take that, it means that the total charge on the chromium should be +12. -14 on the other side becomes +14. +14 -2 is +12. So the total charge for chromium then would be +12. But because you have 2 of the chromiums, then you divide 12 by 2 and you get +6. Okay, and that is how you calculate for chromium in this case. Balancing redox equations. Now this is a little bit different kind of a thing, okay, and electronically means using electrons. This is a little bit kind of a balancing equation than what you do for normal equations. In normal equations, what you would do is add coefficients, okay, in front, and that's how you balance. But if you actually look at this equation right now, it seems balanced in terms of coefficient, but electronically it is not balanced, okay? And what that means in case of redox equations is that the total number of electrons that have been transferred should be equal. So which means that if zinc is giving 2 electrons, then silver should accept the 2 electrons, okay? And if silver is not able to accept 2 electrons, then maybe you need 2 of the silver, okay? And that is how we're going to go ahead and balance this equation. So the first thing you have to do for any kind of a redox equation is to split it, okay, into the oxidation and reduction. So the oxidation numbers, so zinc is 0 and silver is +1 as indicated over here. Zinc as indicated here is +2, and then silver here again elemental state, so it's 0. Zinc is going from 0 to +2. It means it is losing electrons. It is oxidation. Silver is gaining the electrons, and so that is reduction. And then we'll go ahead and write the equation out in terms of electrons. So zinc to give zinc 2 plus 2 electrons, and silver gaining 1 electron to give silver, okay, as in silver solid. Then what you have to do is balance the number of electrons on each side. So if zinc is giving 2 electrons, then silver should accept both of those electrons. Otherwise, you would have more electrons in the solution, which means that we need to multiply this equation, the reduction equation, by 2. And so here we have multiplied this equation by 2. So 2 electrons accepted by 2 silver ions to give 2 silver solid. Okay, so now the 2 electrons that were given by zinc are now accepted by silver. You might think, well, why doesn't zinc just give 1? Well, it's not just capable of giving one, okay? It wants to give only 2 electrons, and that is something that is not debatable, okay? Just like sodium will give only 1 electron, calcium will only give 2 electrons. So zinc will only give 2 electrons, okay? So it's not something that we can debate. So zinc will give 2 electrons, and silver here needs only 1 electron. So that is also not something that we can debate. It is accepting only 1 electron, okay? That is the nature of silver 1 ion, and that is fine. We only need to go ahead and multiply it by 2 in order to show that it is accepting 2 electrons, okay? So you need just 2 of silver to accept those. Then you add up the 2 equations together. So when you add them up, the 2 electrons on the left side and the right side will cross out, and you end up with this equation. So of course this bottom equation now is a little bit different from the top one here that we started with, because now we have 2 silver, okay, which you would not have seen here if you were just trying to do a balancing of equation using coefficients, okay, because this is not that kind of an equation. This is an electronic equation, so you have to balance it using electrons. You will need this a little bit in the lab, and you will do more of it in Gen Chem 2. Here is another example of balancing a redox equation. So you figure out the redox numbers, okay, of each of these elements. So here we have iron 3 iodide and magnesium to give iron and magnesium iodide. Okay, so iron here is +3 because you have 3 of iodide ions over here, and iodine by itself, the iodide ion, each of them is -1. That is how iron is +3. Magnesium here to begin with is 0. Iron here to end up is 0 because it is just an element. And then here magnesium is +2, and then iodide is -1. Okay, so the changes that have occurred in this equation, which means the redox reactions that have occurred over here, are magnesium going to magnesium 2+ over here, so Mg to give Mg2+, and the reduction that is going on is the addition of electrons from or of iron to give iron solid. Okay, so iron 3+ is going to iron 0. So here is that reduction equation. So now again we go ahead and add the electrons as necessary, which means magnesium, which is giving 2 electrons over here, oxidation, and then iron, which needs 3 electrons, adds 3 electrons to become iron solid, and that is reduction. Okay, that's going on. Now we balance the 2 equations. To balance them out, you need to have the same number of electrons on either side. So you need to multiply the magnesium equation by 3 and the iron equation by 2 in order to have 6 electrons on both sides. Okay, so multiplying the magnesium equation, the oxidation equation, by 3 gives us 3 magnesium to give 3 magnesium ions and 6 electrons. And then the reduction equation, which we had to multiply by 2 to get 6 electrons, is 2 iron 3+ 6 electrons to give the 2 iron. And now go ahead and add the 2 reactions up, and you end up getting something like this, which is 2 iron 3+ 3 magnesium, 2 iron, and 3 magnesium ions. Note, in this reaction, we did not write the iodide. Okay, that was a spectator ion, and you can add that, okay, eventually in your final equation. So once you have the coefficients, okay, from balancing the redox, now you can add the coefficients, and you will see that it will even balance out the iodide. Okay, so you don't have to worry about balancing the iodide ion, which was not there in these half reactions. Okay, but that doesn't matter. Okay, it will balance out by itself. So this is how you balance out redox equations. Please go through this again if you need to. You will need it, as I said, okay, in the lab. Some examples of redox reactions are displacement reactions. We talked about this one. I gave you an example before also, where you have a single displacement reaction. So one element displacing the other, like copper here, displaced by magnesium. This is a single displacement reaction. This can be classified as a redox reaction. A decomposition reaction. This is an example of when the oxygen is being removed. Okay, we talked about oxygen being added, but oxygen here is being removed. So if oxygen is being removed, then KCl here has become reduced. Okay, so it has reduced. And you have oxygen as a result. So they have decomposition reaction. Combination reactions are also classified as redox reactions because hydrogen is adding on oxygen, which means that hydrogen is undergoing oxidation. If hydrogen is undergoing oxidation, oxygen must be undergoing reduction. Okay, that is a normal thing to happen. If one thing is undergoing reduction, the other one has to undergo oxidation. That's the whole thing about redox reactions. And then finally, combustion reactions. Okay, in combustion reactions, this is a typical reaction where oxygen adds in. And so carbon, CH4 natural gas burning with oxygen to give water and carbon dioxide. So carbon adds on oxygen, carbon dioxide, so which means carbon is getting oxidized, and then hydrogen is also getting oxidized, but oxygen is getting reduced, okay, in the process. So both carbon and hydrogen are getting oxidized, whereas oxygen is getting reduced. Okay, so these are some examples of redox reactions that you might encounter. So now that you know of all the reactions that are possible, let's go ahead and do some examples. And these are typical questions that you would get from this kind of a chapter, which is, precipitation reactions and acid-base reactions, classify them, and then classify them also in a different way. Okay, so for example, combustion or double displacement and so on and so forth, whatever you can think of. Okay, and so classify them that way. Let's start with the first one, which is H2 plus O2 to give H2O, hydrogen plus oxygen to give water. So in this case, hydrogen is adding on oxygen, and it's a clear-cut case of redox reaction because hydrogen is undergoing oxidation. So this is redox reaction. And this is also called combustion reaction because the hydrogen is reacting with oxygen. Any reaction occurring in oxygen is called combustion reaction. You can also classify this reaction as a combination reaction because hydrogen and oxygen are combining, okay, with each other. So there are three ways to actually classify this reaction. When you have to decide what to classify it as, usually you should classify in the chemical way, okay, which means redox, precipitation, or neutralization. Those are your three best options, unless you're asked to classify them in any other way, which I'm asking you so that you know absolutely everything. But usually the chemical classification is the best one to give. So the first reaction here was the redox reaction. Let's look at this one now. And here we have zinc reacting with sulfuric acid to give zinc sulfate and hydrogen. So basically speaking, this one is a single displacement reaction. And usually single displacement reactions are redox reactions. And if you're not quite sure whether this is a redox reaction or not, you can go ahead and look at zinc. Zinc is 0 over here, the oxidation state, and then zinc's oxidation state here is +2. Okay, and so zinc has given electrons away. So yes, this is a redox reaction and it is single displacement. Let's look at this reaction now. This looks a little bit odd. Yes, we have not seen some of these chemicals before. Well, water you have. This is ammonia, ammonium ion, and then hydroxide in the end. So let me give you a couple seconds to think about this. And if you guessed acid-base, then you're correct, okay? And this is an acid-base reaction, neutralization reaction, because you have hydroxide in here, and here you have ammonia, okay? If ammonia here is a base, then here water must be an acid, okay? And remember we talked about, no, we did not talk about the fact that water can be acid or base, okay? And so here, because ammonia is a base, water is an acid, okay? So yes, we did not talk about this, but in any case, that's what this is. And because you're forming hydroxide here, this is an acid-base reaction. Acid-base reactions are double displacement reactions. Okay, now for this equation, all right, we'll take it one step at a time. Okay, if you have such a long equation to look at, you start with things that you know, okay, which we know, sulfuric acid. Okay, so sulfuric acid is an acid, which means if this was to be an acid-base equation, there has to be a base, and there is no base over here, so which means this is not an acid-base equation, so which means that it is either precipitation or neutralization. So looking at the products over here, we have sulfate, sulfate, sulfate. All sulfates are supposed to be soluble, so therefore this is not a precipitation equation, which means it must be by default then redox equation. Okay, the way you can confirm that this is a redox equation is by looking at one of the elements, specifically the transition element. Okay, so let's look at iron, which is iron is 2 plus over here because sulfate is minus 2, so iron is plus 2. Let's look at iron over here. In this case, sulfate is minus 2 times 3, which is minus 6. Okay, minus 6 divided by 2 gives us plus 3. So iron has gone from plus 2 to plus 3, which means it lost electrons. So yes, this is a redox equation. Okay. Regarding any other classification for this one, well, there is a whole series of displacements going on over here. So we haven't quite learned about that. Okay, so we can leave that as blank. One more equation here, sodium chloride plus lead nitrate to give lead chloride and then sodium nitrate. When looking at this one, there is no acid base over here. Lead is plus 2 over here and lead is still plus 2 over here, which means this is not a redox equation. And then we look at precipitation, and then yes, this is precipitation equation because lead chloride is a precipitate. It is insoluble in water. So this one then is a precipitation equation, which are usually double displacement equations. So hopefully this set of equations give you a little bit of an example of how to classify equations in different ways. To review, we are finishing the different types of chemical reactions in this one. And so you did precipitation reactions before. And in this one, we covered the acid-base reactions, which means the first thing you should know is, of course, what are the acids and what are the bases. So definitely know your acids, bases. And then we talked about oxidation reduction reactions. So you should know all these different keywords in there. What is oxidation, reduction, reducing agents, oxidizing agents. The half reactions, I will probably give you those. I'm not expecting you to master this, but still kind of understand what half reactions are. The activity series that we've talked about is not something that I will ask you in an exam, but you should be able to look at it as far as your homework and any other assignment is concerned.